Hey folks, can people hear me all right? Wonderful. All right, well, let's get started. So announcements for this week, the upcoming deadlines. We have the final homeworks, which is, I believe, 13 and 14 are due on Friday, covering redox reactions and electrochemistry. We will be covering that material today and tomorrow. Tomorrow will be a duplicate of today. There is a significant amount of material this week, and so if I do not get through all of it in the Monday/Tuesday sessions, I will finish it up at the beginning of Wednesday, Thursday. Otherwise, the rest of Wednesday, Thursday will be devoted to Q&A as usual. The group activity, the final one for the semester, is due on Thursday. So that's what the latest post about it announced. The original one where I laid out basically the entire semester for after the latest exam, I think said it was going to be due Tuesday, which is tomorrow. That's not true. It's going to be due on Thursday, and the quiz will open immediately following, and then that will be due on Friday. The goal is for the last midterm to be released on Thursday at 5, not due until a week from Friday, and the 3 parts of the final to be released on Monday of next week, due on Friday as well. Does anybody have any logistical questions before we start getting into the content? I will take that as a no. Okay, so let me share screen. And we will start going through some stuff about redox reactions and electrochemistry. So I have the chat window up, so if any questions arise as I'm going through, please put them into there, and I will keep an eye on that, and we'll try to address questions as they come along. Okay, so let's start by making an analogy to acid-base behavior. So a Bronsted-Lowry acid-base reaction is a proton transfer. And so we can visualize that as what I'm going to show you now. The H plus moves from one species to the other, and we end up with 2 separate water molecules in this particular case. A redox reaction is also a transfer, but it is an electron transfer. And so this is what we should imagine happening. Lithium coming up to fluorine, and then an electron shoots from one to the other, and then by Coulomb's law, by the attraction, the 2 come together. So a redox reaction you can think of as an electron transfer. There is an electron donor and there is an electron acceptor. In this case, the lithium was the electron donor, the fluorine was the electron acceptor. So there are 2 different ways that we can imagine electrons being transferred. One of them is the way that I just described, which where there is a full electron transfer resulting in ionic compounds as a result, or resulting in a change of full charges. So we have the example of magnesium here, giving 2 electrons to oxygen, going from both of them neutral to magnesium 2 plus and oxygen 2 minus, making an ionic compound in this particular case. But there's another kind of electron transfer that can happen where we have covalent bonds. Here we have H2 and Cl2. And in the reactants, since the hydrogens are identical to each other, the electrons in the bond are shared equally, and the chlorines are the same, so the electrons in the bond are shared equally there. But when we have the reaction happen, we see a rearrangement of those electrons to form new bonds between hydrogen and chlorine. Now we have unequal sharing because the chlorine is more electronegative than the hydrogen. And so as a result, we go from a case where everything is uniformly distributed to a case where they are non-uniformly distributed, where the chlorines have more of the electron density than the hydrogens do. So both of these we would like to describe as redox reactions or oxidation reduction reactions, where there's electron transfer of some sort going on. But they are a little bit different in their flavor because one of them is a full transfer and the other is essentially a shift in density. Okay, so let's look a little more closely at this process that we just described. We have the magnesium going to magnesium plus and giving up 2 electrons in the process. And we call that process oxidation. Now notice here that the charge on both sides of the arrow is the same, because on the right-hand side we have 2 negatives and 2 positives, which add together to make it neutral. Now, it is important to recognize here that the phrase oxidation, even though it sounds like it is coming from oxygen, does not necessarily have anything to do with oxygen. It was, for historical reasons, the first examples of oxidation or electron transfer processes that were discovered had to do with oxygen, which is why the name is what it is. But we are really talking about, for oxidation, a more general phenomenon where a species is giving up electrons. Happening simultaneous with the oxidation process is the reduction process. And here we have an oxygen atom that is gaining 2 electrons. And again, we can notice that the charges on the left and on the right are the same because we have 2 minuses on the left, we have a 2 minus on the right. We call this process reduction, and a way to remember that is that the charge is reducing, becoming more negative. Okay. So both of these reactions happen simultaneously. It is not as though we have an intermediate step where the electrons are freely floating around. The two happen in conjunction with each other. And so the combination is known as an oxidation reduction reaction, or to abbreviate it, a redox reaction. Now, a way to remember which one is oxidation and which one is reduction is with the mnemonic Leo goes Gur. Okay, so Leo loses electrons is oxidation. Gur is gains electrons is reduction. So that is a way to remember which half of this is oxidation, which half of it is reduction. All right, so some further terminology. And this, so we just determined that the magnesium is the thing that is being oxidized. The oxygen is the thing that is being reduced. But since they have to happen in conjunction with each other, we can say that the magnesium is the thing that is causing the oxygen to be reduced. And so it is known as a reducing agent. We can say that the oxygen is the thing that is causing the magnesium to be oxidized. And so it is the oxidizing agent. So the reducing agent is oxidized. The oxidizing agent is reduced. When you're talking about it in terms of the agent terminology, you're saying, what does it do to the other thing? Okay, so that's the terminology there. And there's an abbreviated way to say reducing agent and oxidizing agent. They're called the reductant and the oxidant. Okay. So the thing that oxidizes something else is the oxidant or the oxidizing agent. Okay. All right. Now, in order to track whether something is being oxidized or something is being reduced, we use oxidation numbers, also known as oxidation states. We've introduced this previously in the class when we were talking about the strengths of oxo acids, looking at the oxidation number in the of the central atom. But we're going to go through two different ways to calculate this. One of them is the Lewis structure method that we already went through. The other one is sort of a rule-based method. So let's look at some examples of what we want the oxidation numbers to be. So there should be some relationship between the charge on something and its oxidation number. So looking at neon as an example, there's no charge on it, it's not bonded to anything, and so we should hope that the oxidation number should be 0 in this case. Gold. Well, gold is bonded to itself in a solid block of gold, but it's only bonded with itself, and so we expect the electrons should be distributed uniformly throughout the entire block of gold. And so again, we would hope that the oxidation number should be 0 in this case. Magnesium 2+. This is an ion. This ion has a +2 charge. The ion only has one atom in it, so we should have an oxidation number of +2 in this case. Cl2. So in this case, there's no net charge. It's bonded only with itself, so the electrons should be distributed uniformly. So again, we should hope that the oxidation number would be 0 in this case. Cl- is an ion with a single atom in it, -1 charge, so the oxidation number should be -1. All of those, I hope, are relatively straightforward, relatively clear. The idea here is that if you have an ion, then the oxidation number, and that ion is only a single atom, then the oxidation number equals that charge. If you have something that is neutral and it is a single substance, so that the electron density is shared equally, then it should be 0. All right, now let's look at the case that we described a moment ago of H2 reacting with Cl2 to make HCl. So we start with oxidation numbers of 0, and as the reaction occurs, we have a shift in electron density and the electrons are pulled more closely to the chlorines. So what would make some sense here is for the chlorines to become negatively charged and the hydrogens to become positively charged. And the approach we use to assign the oxidation numbers in these cases is similar to how we assign formal charges. So if we assign formal charges and we imagine that there is an electron on each end of this dash that means the bond, then we have for formal charges, we say that the chlorine has a core charge of 7. We have 1, 2, 3, 4, 5, 6, 7 electrons around it, so the formal charge is 0. Similarly, the hydrogen has a core charge of +1. It has 1 electron assigned to it, and so we have the formal charge of 0. But for oxidation number as opposed to formal charge, instead of splitting the bonds equally between the two, we assign both electrons to the same atom. We assign them to the more electronegative atom in the pair. And so, so now we have the same core charge of 7 for the chlorine, but 1, 2, 3, 4, 5, 6, 7, 8, counting both of the electrons in the bond to the chlorine. So we have a +7 and a -8 to give us a -1 formal charge on the chlorine. The hydrogen has a core charge of +1. There are no electrons assigned to it, so we have an oxidation number of +1. So that's the Lewis structure method that we use to assign oxidation numbers. And so here's an example that might be worth spending a moment to go through. So first, practice taking a look at the formal charges on the left-hand side, where what you are doing is assigning 1 electron in each bond to each atom. And on the right-hand side, what you are doing is assigning all of the electrons in the bonds to the more electronegative atom. In a case like the carbon-carbon bond, because those two carbons are the same, you split the electrons equally in that case. So I'm going to give you a moment to try to practice calculating the formal charges and the oxidation numbers, and then I will display the answers to this. While I am giving you time to try this example, if there are any questions about what I've gone through so far, please type them into the chat. Okay, so I hope that you were able to determine that all of the formal charges are 0 in this case. And here are the oxidation numbers. So notice here that the most electronegative element in this molecule is the oxygen. And so it always gets all of the electrons in these bonds. Carbon is more electronegative than hydrogen. And so the hydrogens each get a +1. And then you simply look at how many charges are around each of the carbons. Notice that we have 2 different carbon atoms that have very different oxidation numbers right next to each other here. So one of the things that oxidation numbers can do for you is help you predict what's going to happen in terms of reactivity. So what we can do is imagine that we're bringing into this molecule something that's negatively charged, like a hydroxide ion, and let's see what would happen. You would expect that the negative part of the hydroxide would be attracted toward the most positive part of this molecule, which is this carbon atom right here. And this is indeed the reaction that would happen. And so this is a reaction that you will be learning about if you get to organic chemistry, which is a carbonyl substitution reaction. So oxidation numbers tell you something about where the reactions are going to happen that formal charges don't. And so formal charges are what you use to determine which Lewis structure is the best Lewis structure, or to determine the contributions of different Lewis structures in a resonance structure. And oxidation numbers tell you something about which atoms are holding the electrons most tightly and which atoms grab electrons from which other atoms as we look at oxidation numbers changing over the course of a reaction. Okay. A second approach to calculating the oxidation numbers or oxidation states is a rule-based method. And so this is a method that is in some senses faster than the Lewis structure method. It is useful in cases where you don't necessarily know what the Lewis structure is going to look like. But these rules that are being used here are based on the same principles that we've already talked about. So an atom in its elemental form has an oxidation number of 0. We've already talked about that. A monatomic ion, the oxidation number is the charge of the ion. For any molecule or ion that has a charge, the sum of the oxidation numbers should equal the charge on the ion, or if it's a molecule that doesn't have a charge, then all of the oxidation numbers within the molecule should add up to 0. So that makes sense because oxidation numbers are simply an accounting system for the charges. And so hopefully the accounting system will add up to the same thing that is the charge on the unit that you're talking about. Now, within a structure, within a molecule or an ion, we have group 1A. So that's going to be the alkali metals, have an oxidation number of +1 in compounds. And that should make sense because things like sodium, potassium, and lithium tend to form compounds where they have a +1 charge. For group 2A, so calcium, magnesium, and so on, have a +2 charge, and so they have oxidation numbers of +2. Hydrogen has a +1 when it's in combination with nonmetals, and a -1 when it's in combination with metals and boron. Now, let's think about that in terms of our Lewis structure method. Well, hydrogen is less electronegative than nonmetals. It is more electronegative than metals and boron. So the -1 and the +1, excuse me, the other way around, the +1 and the -1 makes sense from the perspective of electronegativity. Now, what is the most electronegative element in the periodic table? It's fluorine. So whenever it's in a compound with something other than fluorine, it's going to grab the electron in its one bond, and so it's going to be -1 always. What's the second most electronegative element? Oxygen. Well, oxygen in compounds that don't include fluorine, it's going to have a -2 because for both of its bonds, it's going to grab both of the electrons. An exception to that is a peroxide. A peroxide is a case where you have an oxygen atom bonded to another oxygen atom. And so in that case, that oxygen-oxygen bond is going to be split equally. And so that one becomes it's going to be a -1 in those cases. For group 7A, so the halogens, it's going to be -1 in combination with metals and nonmetals except for oxygen, and other halogens lower in the group. So the halogens, chlorine, bromine, iodine, and so on, tend to have a -1 charge. So these are the general rules that you can follow. And so I might recommend doing like a screenshot of this so that you have the table that you can work with. I don't know how to do that on a Mac. On a PC, if you hit the print screen button, you can then open something like Word or something and do a paste, a Control-V, and you'll have this picture for you. We're going to be using this in over the next few slides that we're going to be going through. So I'll give you a moment to do that. Thank you from the chat. Command-Shift-4 on a Mac to do the copy. Sarah says Command-Shift-5, so I don't know which of those it is, 4 or 5. At any rate, I will give you a moment to figure it out and paste it somewhere. We're going to be coming back to this. You're going to be using this on some example compounds and some example reactions in just a minute. And I apologize to the class for not being more Mac literate. All right, so let's do some examples here. We're going to go down in this order, down the column and then down the next column. So ZnCl2. So the formula unit is neutral. Chlorine is a halogen, and so it's going to have a -1 charge for each chlorine, which means figure out what the zinc should be. Hopefully you can see that the zinc would have to be +2. Each chlorine is a -1. Yep. And so that will make the total of the charges for the molecule or the species to be 0. Now, the convention, and this is something you need to get used to, the convention is to write the oxidation number for a single atom over the atoms rather than the total of them. Because what we're going to be doing is looking at in a reaction how individual atoms change oxidation number. And so you don't put a -2 over the chlorine because there are 2 of them. You put a -1 because each chlorine is a -1. Okay, let's now look at the SO3, the next one down. Now, and I will tell you in this molecule, each of the oxygens is attached to the central sulfur. This is not a peroxide. So think about what goes for the oxygen, and then think what the sulfur would have to be. So hopefully you can see that each oxygen will be a -2, meaning that all of the oxygens together will be a -6. So the sulfur is going to have to be a +6. Okay. All right, let's look at HNO3, which is nitric acid. And you should remember this from the oxo acids component of the class. The nitrogen is the central atom. There are 3 oxygens around it, and the hydrogen is going off of one of the oxygens. So in this case, these are all non-metals. So the hydrogen should be a +1. Each oxygen should be a -2. And so see if you can figure out what the nitrogen should be. And hopefully you were able to figure out that it should be a +5. So the total of the positive charges is 5 and +1 is 6. The total of the negatives is -2 times 3, so -6. All right, SC2O3. This is, again, not a peroxide. I will tell you that on any exam question any exam question that I provide, if it is a peroxide, I will tell you. If I don't tell you, it's not a peroxide. Okay, this one is not a peroxide. So we should have -2 times 3 for -6, meaning that each scandium here is going to be a +3. Gallium chloride, hope you're gaining some speed with this. The chlorines where your eyes should go first. It's a halogen, so each one should be a -1, making the gallium a +3. HPO4 2-. So this is our first example we're doing where there's an overall charge on this on the species. So this is an ion. So each oxygen, as before, is a -2. The hydrogen is a +1. And the total of all of the charges has to add up to a -2. So our oxidation number for the phosphorus has to be a +5. So we have +5 +1, it makes a +6 total. -2 times 4 is a -8. And so that added together becomes the -2 charge. IF3, so this is an interesting one where we have 2 different halogens, but remember that fluorine is the most electronegative element on the periodic table. So, fluorine's rule takes precedence. Each fluorine is a -1, meaning that the iodine has to be a +3. And that is despite the fact that iodine has another rule in the list that says, oh, it's often a -1. So there's a precedence, and that precedence is based on electronegativity. Okay. So let's now look at a couple of reactions to see if they are indeed redox reactions or not. And what we do for this is we simply go through and assign oxidation numbers to everything. And we see, do they change or not? And if so, what changes? So I'm going to give you a minute to do both of the oxidation numbers for both of these. This is a skill you should practice until you can do it quickly and accurately. All right, so for the first one, the oxygen's a -2, so the calcium has to be a +2. The oxygen's a -2, so the carbon has to be a +4. The oxygen's a -2, the calcium, because it's a group 2 element, has to be a +2, so the carbon has to be a +4. Do any of the oxidation numbers change over the course of this reaction? That's right, they do not. So the top reaction is not a redox reaction. Now in the bottom one, let's look at our oxidation numbers. So the oxygen's a -2, the potassium is a +1, so that means the nitrogen has to be a +5. On this side, we have the -2 and the +1. These are elements by themselves, so those are both zeros. So we do in fact have oxidation numbers changing in this case. So what we have is the nitrogen has an oxidation number decreasing, so that is the reduction process. We have the oxygens that are that have oxidation numbers increasing from -2 to 0, so that is the oxidation process. Okay. One of the important things to learn how to do with a redox reaction is how to balance the equation. Now, this is trickier than most of the balancing of equations that you've seen so far. In this case, notice that it's particularly difficult because we have nitrogen only in one place on the left-hand side. We have nitrogen in 2 different places on the right-hand side. And so it's kind of hard to know how to balance this as we go. But using our oxidation numbers, we can figure out how to do this. So let's take a look. Let's first assign our oxidation numbers. I'm going to give you a moment to do that here. In order to do that in this case, you need to remember that the NO3 ion is has a -1 charge. And so in the copper nitrate on the right-hand side, there are 2 nitrates, each with a -1 charge. So step A, assign oxidation numbers. 0 for the copper because it's an element, -2 for a total of -6. We have a +1, and so the nitrogen has to be a +5. On this side, we have 2 nitrates where it's a -1. So this is a +2, and we can split inside what each nitrate is. -2 times 2 is -4, so that has to be a +4. A -2 and 2 +1s, so that works out. Identify the oxidized and reduced species. So like I did before, I'm going to draw arrows. Oh, and we're going to use Leo goes GER to remember loses electrons oxidation, gains electrons reduction. So copper goes from a 0 state to a +2 state. The nitrogen goes from a +5 state to a +4 state. And notice that some of the nitrogen does not change oxidation number. So there's some reduction going on, but then there's also some nitrogen that is not. Okay. Next, we identify the number of electrons transferred. So for the oxidation of copper, it's going from 0 to 2. So we have 2 electrons that happen here. For the nitrogen, going from +5 to +4, we have 1 electron that's getting transferred. But however many electrons are being lost by the copper, we have to have the same number that are being gained by the nitrogens, which means that we need to have 2 of this happen for every 1 of this. We have to have 2 reductions for every 1 oxidation because they have, it's 2 electrons to 1 electron. So we multiply this part by 2, meaning that we double the amount of HNO3 and we double the amount of NO2. So we put 2's in front of those. Once we have the electrons balanced, we start looking at the other elements. So we've got copper here. The only place copper goes is here. So that means that if we have a 1 here, this has to be a 1. Now we have 2 nitrogens here, plus the 2 nitrogens here that are fixed, meaning that we need to now have 2 more nitrogens over here. So this has to become a 4 because 2 of them go here and 2 of them go here. Now what we need to figure out is the hydrogens and the oxygens. Well, the hydrogens, there's only 1 place of hydrogens. We now have fixed what this one is. So we need to have 2 waters. And now we should double check to make sure that that once we have the 2 waters, that we have the right numbers of oxygens on both sides. 4 times 3 is 12. We have 12 oxygens on the left. 3 times 2 is 6. 2 times 2 is 4, so that's 10. 2 times 1 is 2 for a total of 12, and it worked. So by using the oxidation numbers, we were able to figure out how to balance an equation that's relatively complicated where the nitrogen is going to 2 different places. Okay, so here's an example. We should, and we're going to practice this. So step 1, remember, is to assign the oxidation numbers. The PBS is an interesting case because PBS doesn't have anything on the rules, does it? But what group is the sulfur in? It's in the same group as oxygen. So we have we have an element here that is probably going to act similarly to oxygen, given that it's not attached to anything that's particularly electronegative. So we assign our oxidation numbers like this. We figure out what is being oxidized and what's being reduced. And sulfur is going all the way from a -2 to a +4. I mean, that's huge. 6 electrons are changing places. And the oxygens are all going from a 0 to a -2 state. So we have, since there are 3 oxygens on the right-hand side, we have a total of 6. And so this one actually already has the right number of electrons, but we now need to make sure that we have enough oxygen atoms to add up to 1 and then 2 here for a total of 3. So we put a 3 halves in front of this, And then we finish the balancing by getting rid of the fractions and multiplying everything through by 2. And that's so that we have now balanced this, this reaction, which again is a little bit complicated because the oxygen is getting split amongst 2 different places. All right, here's another example. Let's go through this one. Assign the oxidation numbers. All right, let's see how you did. So the most complicated one here is probably the K2Cr2O7 because we're dealing with some big numbers. So the oxygen has to be -2, so we have a whole -14 to deal with. Potassiums are +1, so that leaves us with 12 more. And so each chromium has to be a +6. We now identify what is oxidized and what's reduced, who's changing oxidation state. Hope you can see that the chromium is changing from a +6 to a +3. Let's work our way through this. And the iodine is changing from a -1 to a 0. But notice that some of the iodine is not changing state. Now let's walk through this. Now, notice that the chromiums that are coming across here, there are 2 of them on the left, so we have to have 2 of them on the right. So we put a 2 there as a starting point. We notice that the iodine that's going from here to here, there are 2 of them on the right, so we need 2 on the left. So we put a 2 here temporarily because we now need, we recognize that's going to go up because we have to take into account these iodines as well. But first, we're just dealing with the oxidation and the reduction portions. So we see that for the 2 chromiums total, we have 6 electrons that are being transferred, 3 each for the 2. In this case, we have 1 electron for each iodine that's happening for a total of -2. So we now need to multiply the oxidation step by 3 so that we get +6 and -6 so that the electrons balance out. So times 3. And so we now have this equation. And at this point, we now deal with the parts of this that are not the redox components. So a place to start is to notice that the potassium chromate, so we have the chromium fixed already because the amount of chromium is determined by how much chromium we have over here. That means we have to have 2 potassiums. So that means that, so I was just saying that it's fixed by this. This one is also fixed based upon how much is, because this is all of the iodine that has been changing oxidation state. We now have to have a 2 in front of the potassium iodide so that we have 2 potassiums that are going across here. And now that one's fixed. Now we look here and say all of the iodines on the right are fixed. So we have 1, 2, 3, 4, and then 6 more for 10 iodines on the right. So this has to have 4 more over here. And so that's going to go up to a 10. I did this in a different order, apparently. We also look at this and say the only oxygens on the left are here is for 7. So we need 7 oxygens on the right. The only place there are here. And so this has to go up to 14 in order to account for the 2 plus 6 makes 8, plus 6 makes 14 iodines. We also have 7 times 2 hydrogens, so it adds up to 14 hydrogens here. So going through and determining what's fixed so far, and then seeing what that means about the others lets you assign the others. So we get our total reaction that looks like this now, which is quite complicated because notice we have iodine here, and it's going to 3 different places on the right-hand side. But yet we were able to figure it out based on oxidation numbers. Now, this is how you go about balancing a redox reaction in a case where you're given all of the components. But there are some cases where you're not. And so there is another method called the half reaction method that we can use to balance a redox reaction where we're just given the species that are changing oxidation state. And so we have dichromate going to chromium. We have the iron going to iron here. The process for this, this is the one that is described in the text, is to write the two half reactions. And that's a phrase we're going to come back to quite a few times. The oxidation half reaction and the reduction half reaction. So we see that the iron is going from iron 2 to iron 3, and we have the chromium is going from the dichromate to the chromium 3+. We balance everything except the oxygens and the hydrogens. So in this case, because there are 2 chromiums on the left, we have to have another chromium on the right. Next, we balance the oxygens by adding water. Okay, so we now have water happening here, 7 of them, in order to account for the 7 oxygens that we have on this side. Then we balance the hydrogens by putting H pluses. So in this case, we had 14 hydrogens on the right. We need 14 hydrogens on the left, so put in H pluses. We now balance the charges by putting in electrons. So in the first case, in order to make the left-hand side and the right-hand side have the same charges, we need another electron on the right. In the bottom case, we have a 2 minus and then 14 pluses, so that's a total of 12 pluses on the left. We have 2 times 3, 6 on the right, which means we need 6 more electrons on the left. We balance the electrons across the reaction. So this is like in the previous examples where we said we needed to, if we were losing 6 electrons and gaining 1 electron, we needed to multiply through by 6. We're doing exactly the same thing here. So because we have 6 electrons transferred in the bottom step, we need 6 electrons in the top step, so we need to multiply the top step by 6. We add the 2 reactions together and cancel anything that's on both sides. And so in this case, the only thing that's on both sides are the electrons, so those cancel out. But there can certainly be plenty of cases where you may have water on both sides, or you may have H pluses on both sides. And so here we now have our balanced reaction that is happening under acidic conditions. Now, it may very well be, however, that you are told that the reaction is happening not under acidic conditions, but under basic conditions, in which case there's a further step. If you do that, you take this reaction, and if it's under basic conditions, you add hydroxide to both sides to cancel out the H pluses. So here you would add 14 OHs to both sides. The 14 OHs on the left will combine with the 14 H pluses to make 14 H2O. And then we have 14 OH minuses on the right, but we have some H2O on both sides, 7 and 14, so we get rid of those, so then there would be 7 waters on the left. So this is the balanced reaction. That's the same redox reaction, but now this is how it happens if it's under basic conditions rather than under acidic conditions. Okay. And then it's always a good idea, because these can be complicated, to check that everything's balanced. 6 irons, 6 irons, 2 chromiums, 2 chromiums. Count up the oxygens. You've got 14 plus 7, so 21 oxygens here. Nope, I didn't do that right. I was counting 2 of that. So 7 and 7 makes 14. There are 14 here. Hydrogens, we've got 14. We've got 14 hydrogens. So everything there works. Probably a good idea to check charge as well. We've got 6 times 2 is a plus 12. Minus 2 makes it plus 10. On this side, we have 14 minuses with 6 pluses makes 14 is 6, so 8. And then we have 6 times 3 is 18. So we end up with a plus 10 on the right as well. Okay. So that's redox reactions. We're now ready to talk about electrochemistry. How am I doing here? Wait a minute, 10:30? Okay. No, we still have some time left. Okay. We're now ready to talk about electrochemistry. Electrochemistry is when we take the two half reactions and we separate them. So they're happening in two different places. Now, I initially introduced redox reactions by saying that they both have to happen simultaneously in order for the reaction to occur. And that's the case. That is exactly correct. But if we separate where those two reactions are happening, and then we connect them by a wire, then the electrons flow along that wire. And that is how an electric current is generated. And so what we are looking at right here is a battery. This is making a battery. Now, so let's look at what's happening in this particular case. On the left-hand side, we have the oxidation half reaction. We have zinc going to zinc 2+ plus 2 electrons. What's happening is that our electrode, the metal rod of zinc that is stuck into the solution, is kind of dissolving, giving off 2 electrons, which then travel along the wire. We now, whoops, I didn't mean to do that. Let me back up. The electrons that come across here come to the reduction half. And so at this side, the electrons join with copper ions that are in solution to deposit copper onto the surface of the copper electrode. And so in this case, on the left-hand side, the zinc electrode will slowly go away as it deposits zinc into the solution as zinc 2+ ions. On the right-hand side, copper from the solution is getting deposited onto the copper electrode, making the electrode larger as a result. Now, if that were the only thing that were happening, then we would be building up a negative charge over on the right-hand side, and we'd be building up a positive charge over on the left-hand side. We can't do that. We need things to remain electrically neutral. And so we have to introduce this orangey thing here, which is called a salt bridge. And so what happens in this is that there are dissolved ions. And so if the negative charges are getting deposited on this side because of the current that is passing through the wire, then building up a negative charge here, which will make the potassium ions in the salt bridge flow to the right to balance out the charge, and the chlorine ions will travel to the left to balance out the positive charge that's being generated on the left-hand side. So if you did this without the salt bridge, there would be no current flow. But you put the salt bridge in place, there will be a current flow, we can measure the voltage across it, and we have a working battery. All right. So some terminology and some relationships that are going to be important to learn here. The electric charge that we're dealing with is measured in coulombs. The SI unit for electric charge is the coulomb, and it comes in units of single electrons. I mean, this here says it's the charge on a proton, but it's also the negative of the charge on the electron. And so this is the magnitude of that value. Electric current is the movement of charge. It is the charge per unit time, so coulombs per second. And it's known as the ampere is 1 coulomb per second. And so that is measuring how many electrons are flowing along the wire per unit time. Electric potential is the force with which they're moving. So, and this is measured in volts. And that is joules, the amount of energy per coulomb or unit of electric charge that is flowing. And so you could have a high current but a low voltage, which would mean that the electrons are traveling very fast, but not with very much force, not with very much energy that they are traveling. You could have a large voltage but a very low current, meaning that there aren't many electrons flowing. They aren't going very fast, but they're going with a lot of force. Or you could have other combinations of those as well. And then we've already talked about electric field. I don't know why that's particularly in this one, in this table from the text. Okay, there are several different types of electrochemical cells, and being able to tell the difference amongst these is going to become important. So the first type is a galvanic cell, also known as a voltaic cell, and that's the kind I just showed you. This is a case where the redox reaction is spontaneous. It produces electrical energy, and it is what is used to make a battery. It is also the driving force behind corrosion. So if you have an iron bar that is corroding to become rust, that is actually a galvanic process that is happening, an electrochemical redox reaction that's happening. We'll talk about a little bit more of that in a moment. A concentration cell, and unfortunately this is, I don't think, even mentioned in the textbook, but Newton goes over this. This is a galvanic cell where both of the half reactions are the same, but one of them is the reverse of the other. So maybe you have iron 2+ going to iron 3+ on one side, and iron 3+ going to iron 2+ on the other side. The issue is that the solution, the iron solution that you have, is going to be at different concentrations. And so that concentration difference is what's going to drive the reaction one way or the other in that case. We have fuel cells. All of these we're going to go into more detail on in the next few slides. Fuel cells, which are similar to galvanic cells, but there's a fuel that flows into the system, and then there are waste products that flow out of the system as you do it. So if you imagine having, if you imagine the reaction happening in the galvanic cell I described earlier, where I think, what did we have, zinc and maybe copper, if I remember correctly. I don't remember what we had. But you could imagine that the concentration of the zinc and the copper would be changing as that happens. And so if you have sort of the flow of copper or zinc into or out of the system in a way that allows the reaction, the concentrations to stay the same over the course of the reaction, and that would be a fuel cell. And then we have electrolytic cells, where, and the process is called electrolysis. This is where you have a reaction that is non-spontaneous, but you're applying an externally applied voltage or current across it to drive the system the other direction, making the process spontaneous. So this is what happens when you recharge a rechargeable battery. It's used in a couple of different ways. One of them would be to generate specific elements or compounds, to synthesize elements or compounds that are hard to get by other methods. And it's also used in electroplating. We'll see examples of that in a minute. Okay, so let's look at some examples here. So we're going to start with the galvanic cells up here, which we already looked at an example of, and we're going to use that to develop a lot of the concepts. So electrons flow from anode to cathode. And the convention in these diagrams is to put the anode on the left-hand side, so that the flow of electrons is going from left to right. So this means that we have the oxidation process happening on the left, and we have the reduction process happening on the right. The way these are labeled, the anode and cathode, is whether the anions in the salt bridge are flowing towards it or the cations are flowing towards it. So anion, remember, is the negatively charged ions. So the anions in the salt bridge flow toward the anode. The cations in the salt bridge flow toward the cathode. And then we can abbreviate this whole diagram that we have with what's known as cell notation, an electrochemical cell notation, where we are writing the process that's happening as though it's moving from left to right. So copper is turning into copper 2+, meaning that electrons are being released, which are then flowing away from it. The vertical bar means there's a phase barrier here. And so there's a phase difference between the copper solid and the aqueous solution of copper 2+. We have a double vertical line here, meaning the salt bridge. Then we have the silver ions, which are in the aqueous solution at 1 molar concentration, that are picking up the electrons that are flowing in to form the silver solid depositing onto the surface. So we have the copper flowing this way, we have the silver flowing this way. The copper is going from copper to copper 2+, the silver is going from silver plus to silver. That's how this notation works. The voltage that is measured across this is a function of what these two reactions are, and we will get to that in a moment. All right. So, sometimes we have an electrode that does not participate in the reaction that's happening. So in this case, for example, we have hydrogen gas flowing in, and we have, in this case, a platinum electrode. And what's happening is the hydrogen gas is giving off some electrons, which are giving off some electrons. And we have the H+ ions being the result of this, except that's not what's written down here. So let's look at what's happening here. We are saying that the magnesium is forming the Mg2+. So we have deposition, we have the magnesium coming off into solution, which means that the electrons are flowing this way. And so what's happening with the electrons flowing this way is that they are combining with the hydrogen plus and are forming H2, which is then bubbling out around here. So this platinum electrode is an inert electrode, meaning it's a surface at which the reaction is happening, but it's not actually part of the reaction. And so we include that in the cell notation as a further component. And what's wrong with the picture at this point? Well, in the previous slide, we talked about the convention being that you put the anode on the left and the cathode on the right, so that we are looking at the flow going from left to right in the cell notation. Well, this was drawn backwards. And so this is a good example of where, you know, I found this, this picture online. I just searched on inert electrodes, and this was one of the first pictures that came up. I pulled it into here, and then I realized, oh, you know, it's drawn backwards. It should be flipped horizontally. Which is a very good reason to not just try to Google answers for things. All right, and so we have the oxidation reaction, we have the reduction reaction, and the overall reaction shown here. Oh, I didn't put in an arrow on that. I apologize for that. Okay. Now, the particular electrode I just showed you, where we have the hydrogen gas, we have a platinum electrode, and we are having the reaction between H+ and forming H2, or vice versa. This is what is known as the standard hydrogen electrode, or the SHE. So, and it is the standard hydrogen electrode under conditions where the acid concentration is 1 molar of HCl, meaning that since that's a strong acid, it's 1 molar in H+. And the pressure of H2 is hydrogen, it is 1 atmosphere. We define this half cell potential to be 0. That's a definition because we cannot actually measure the potential of a half cell independent of anything. It has to have the other half cell in order to measure a voltage that's going across it. So by defining this as our standard potential, our standard hydrogen electrode, then all of the other half cells that we attach to this, when we measure the voltage that's across it, that becomes our measurement of the voltage of the other half cell. So we designate these standard conditions where all gases are at 1 atmosphere and all concentrations are at 1 molar by the little degree symbol that you see here. And so if we take our standard hydrogen electrode and then attach it to another electrode, another half cell, in this case, we are attaching it to a copper 2+ going to copper solid electrode. And if we have our concentration of copper 2+ at 1 molar, then we're under standard conditions. Then very simply, the voltage of the cell is equal to the voltage of the cathode half cell minus the voltage of the anode half cell. And we've defined this standard hydrogen electrode half cell to be 0 volts, which means that the voltage that we measure here is going to be the half cell voltage for the copper 2+ electrode that we have here, 0.337 volts. And if we then measure one thing on this side and then swap it out and measure something else on this side and then connect those two together, indeed we find that the difference of the two becomes the voltage that we end up measuring. So this relationship empirically ends up working. Okay. All right. And so when we do that, we can then come up with a set of half cell voltages, which are written in the reduction direction. If the reaction that's happening is actually the oxidation reaction, which means that we're going from what is products here to what is reactants on the other side, then in that case, we simply take the negative of the potential that we have listed here. So reduction potentials are what is tabulated. And so what we do is we take the cathode reduction potential minus the anode reduction potential to get the overall cell reduction potential. So if we were to have one half cell be silver going to silver plus going to silver solid, and if we have then the zinc electrode going on the other side going from zinc to zinc 2+, then we take our plus 0.8 minus the negative, so plus 0.76, and we get an overall cell potential of 1.56 volts. And so if you took those two cells and connected them to each other, that is the voltage that you would end up measuring. So let's now look at some equations. Okay, so we'll have a little bit of time. Okay, so the charge on a mole of electrons is Faraday's constant. So this is the value of it. It's in coulombs per mole. The electrical work that happens is the total charge multiplied by the voltage that you have across it. And it is also equal to negative of the number of moles of electrons in the balanced redox equation times Faraday's constant, so that you can get the total charge. And the E cell here is the voltage. If this is the work, well, we said earlier in the earlier section, last week's material, that the maximum amount of work that can be done by a system is delta G. That's why it's called the free energy. It's the energy that you can take and make into the work. So delta G is going to equal this value here, NF E cell. That should have been a subscript. I apologize for that. Now, we also have a relationship between the between delta G and the equilibrium constant. You remember that from last week? So that means that we now have a relationship between the standard cell potential and the equilibrium constant. And so solving that for E cell, we can find RT over NF times natural log of K. So we've got this relationship here, this triangle over here, that shows how to convert among the standard Gibbs free energy, the standard cell potential, and the equilibrium constant for any redox reaction. This triangle is in the textbook, so don't scramble to write it down right now. You can find it in there to work with. So this is what we do if we are looking at standard conditions. how do we move to non-standard conditions? Because we're not always going to have 1 molar of whatever we're dealing with. We're not always going to have 1 atmosphere of whatever gas we're dealing with. Well, so this is just what I had before moved up. Remember that for delta G, we were able to relate the Gibbs free energy change to the standard Gibbs free energy change by this expression, where we add in RT, ln Q, where Q is the reaction quotient. Well, so we now know what delta G is from up here, minus NF E cell. So I'm just plugging that in. Well, this is just the same thing, but under standard conditions. So we can just bring those two down here. And now let's divide through by minus NF, remember F is Faraday's constant, to find the cell potential, meaning the voltage that you'll measure across the cell, equals the standard cell potential minus RT over NF times the natural log of the reaction quotient. This equation is known as the Nernst equation, and it tells you how to determine the cell potential under any non-standard conditions you want. Now, when you look up the Nernst equation in a lot of sources, you will very frequently find the RT over F part already combined at 25 degrees C, and they'll just have some kind of voltage per mole that's listed across here. I prefer it in this format because it lets you calculate it at different temperatures. But regardless, this is either way ends up working if you're at 295 Kelvin. I also need to make a note here. N, what do I mean by N? Number of moles of what? That is the number of moles of electrons in the balanced redox equation. So if it was 6 electrons being transferred that you had, and we multiplied one of the either the reduction process or the oxidation process by 6 in order to balance the number of electrons, that's what we're talking about. We're talking about the number of electrons that are being transferred. Okay, let's see. The rest of this is going through examples of different kinds of cells. So different types of cells. So I'm going to do that part at the beginning of class on Wednesday and Thursday. And we have a few minutes where I can answer some questions if anything so far hasn't made sense. I'm gonna turn off the, if I can figure out how to do this, I'm gonna turn off the prohibition against people unmuting themselves. If people have any questions, please speak up or type it into the chat. We have a few minutes so we can go over some stuff. All right, not hearing any questions. So we will on Wednesday/Thursday go over the remainder of the material. Primarily, that's going to be looking at some examples of different types of cells, including concentration cells and fuel cells and electrolytic cells, where we look at things like electroplating or generating elements or compounds that's hard to get otherwise. And we also will look a little bit at the stoichiometry of electrolytic cells. And I think the other thing is talking a little bit about corrosion as an example of a galvanic cell process. And then after that, that won't take anywhere close to the whole time on Wednesday/Thursday. So we'll have Q&A, muddiest points, those sorts of things on those days. Thank you all, and I'll see you later.